model. Again, we'll come back and so this is where we are talking about the similar type of model, right? And we'll come back and see that okay, how to combine few models and get the best result, right? So that part will cover during enterprise minor. So today's discussion point is that if I have 4 or 5 ways, right, to create model, right, I can take all 8 variables, and that is somewhere the basic way of comparison is that wherever your adjusted R square is kind of highest, right? So that shows that okay, model explainability is higher. Apart from adjusted R square, is there any other parameters? Is there any other way where we can compare models? Just think about that scenario which you have run that problem, right? You have just run a single model with lot of other variables, right? So in one model, you might have taken all the 8 parameters, all 8 independent variables, or all 6 independent variables. In another model, 5, in another model, 4, 3, like that. So what the software has done for you, different combinations it has run for you, and on each combination it has showed that okay, what is the adjusted R square, and based on the whichever model is providing with the best adjusted R square, that model has been selected, right? So that is the one way to do it. Understanding adjusted R square, which we discussed last class. Then what are other ways? Other ways that because you have a let's say 16,000 data point for different customers. One way is to kind of divide them into different data sets, training, validation, and testing data set. Then whatever model you are building in training data set, try to run that in a test dataset and see that whether whatever adjusted R square or whatever parameters you got in your training dataset, is it obviously it will not be exactly same, or it most of the times it will not be better. It might be little worse. But how much? Let's say in the training dataset, let's say out of 16,000 rows, I have not created any validation dataset. Let's say 10,000 is my training dataset, 6,000 is my testing dataset. So in my training dataset, adjusted R square for a model is showing zero point 0.8, but when testing is happening, it is showing zero point 0.7. So what happens in my testing actually is a real-time dataset. My explainability is coming down by 10% because from zero point 0.8 to zero point 0.7. So in that case, I have to think that whether I can deploy the same model in the actual production dataset. But if let's say the variation is very small, you got zero point 0.8 and in your testing dataset you are getting close to 0.78 or 0.77, then still you can go ahead and say that okay, reliability is good and I can go ahead with the existing model. So that is one way where we are creating data partitioning, training, testing, validation. Today we'll discuss why validation dataset is sometimes required, right? Training, testing, everybody understand. I have a 100 rows of dataset or 1,000 number of data points. Out of that 800 data points, I'll go and create a model, right? And based that model, I'll test on the those remaining 200 data points, right? Then there is something called resampling methods. So whenever you have smaller data set, because when you talk about training, validation, test data set, right? Ideally, you should have a large data set. So there is no common kind of understanding what do you mean by large data set. So you can think of in terms of, let's say, if it is talking about customers, at least 10,000 or 20,000 data points. But again, there is nothing written that, okay, this is the minimum data point required. There are many different sample size calculations for multivariate analysis. So generally the minimum is required, but what is the requirement is not there. Let's say if I'm running a multivariate regression, right? So the point is for each variable, if I'm putting into my data point, at least 15 to 20 rows of data should be there. So that means if I have, let's say, 10 kind of predictors, that means independent variables. So at least my data set should be 150 to 200 kind of rows, 150 to 200 data points should be there. So 15 to 20 per each predictor. But again, it is a thumb up rule. So there is no kind of a rigorous mathematical calculation where you say for a univariate, bivariate, that is there, but for a multivariate, there are a lot of debates. What should be this kind of normal or minimum data size? And then resampling methods. Resampling methods is when you have a small data set. Let's say rather than 16,000 data points, which I gave you, you have only 100 or 70 data points, right? So that is where what it say you like keep like your model will randomly select 10 data points, or let's say 30 data points as training, 40 data points as test. So in the first case, what you used to do, training and test data set selection happens only once, right? In the beginning itself, your model will divide that whatever 10,000 or 16,000 data set into two parts, training and testing data set. The model will build on the training data set and will get tested in the testing data set. But in the resampling methods, what happens? Let's say I have a very small data set, 100 data points. So automatically it will keep running. Randomly 10 or 50 data sets or 30 data points will be chosen as training. The remaining 70 will be testing, or 70 will be chosen as training, 30 will be chosen as testing. Then that 70-30 will keep changing, right? So it is a kind of iterative. So the training and testing selection keep on continuing, and each time whatever model you get, right, at the final model or the final answer will be the average of all these model parameters what you are getting, right? All these whatever model, let's say hundreds of model was created, the average of that will be your final model. So basically it is averaging out your errors, averaging out your problems or the bias in your models, right? So that is another way. Then there is something called the information criteria. It is similar to your adjusted R square. Adjusted R square only talks about the error part, right? Adjusted R square talks about how much model complexity you can explain and how much you cannot explain, right? Here, when you talk about information criteria, right, and I'll show you few of them. No need to remember the formula because the software itself will calculate for you. Only thing what you have to remember, how you are going to use that. So there are a lot of parameters like adjusted R square, which you can use to compare different model performances, right? So most of the times, if the value is smaller, that model is performing better, right? So let us try to understand one by one. Training, testing, validation data set. So if you go and look into your predictive regression model, so there is an option to partition the data. Let me just quickly see that whether that is open or not. Yeah. So if you go to, and last time also you must have run this predictive regression model. So if you, so today, what is the additional thing what we are going to learn? Let me show you that. Okay. So validation data set and test data set, you have to select here, putting the proportion, right? So let's say I have a 60% training data set. That means either I can put validation data set as 0 and training testing data set as 0.4, or let's say 0.2, 0.2, or 0.3, 0.1, right? So in the class exercise, what I've asked you to do, 20% as validation data set, 20% as training data set, sorry, testing data set. That means your training 60% of the data will be taken as training data. But what we are going to discuss today is selection part. How do you select different methods of model creation, right? So forward selection, backward elimination. So forward selection is, I'll start with a simple model, right? So let's say I have one dependent variable, which is customer's revenue, and other independent variables, number of subscription from customers, age of the customer, customer's income, gender, all those information is available. So one by one, I'll take one variable, try to create a model. If that is giving me good answer, then I'll take another variable, right? So forward or stepwise, in the stepwise regression, when you talk about forward selection, we start to predict our dependent variable by taking one by one. So we start with a simpler model, then bring another variable. Like that, it is a forward selection. Backward elimination is when you put all the predictors, all the independent variables in the model, right? In the your first model will be the most complex one. So all your independent variables will be put together to predict your dependent variable. Then one by one you start to take out which one you will take out, whichever is not significant to your model, where p value is greater than, let's say, 5%. Then stepwise regression. In stepwise regression, you have to mention which variable, like it gives you option that okay, you take, or model automatically randomly selects, right, which one the like kind of which model, which kind of variables to take forward, right? uh, So then if you see the next four, lasso, adaptive lasso, elastic net, and least angle regression, that we have not discussed so far. Today we are going to discuss because that happens to be right something to do with your the concept of bias and variance, which we'll discuss, and after that we'll discuss those four models. But don't worry about it when I talk about those models. Just remember what is that, right? Not the mathematical formulas, because that anyhow software will help you to calculate, right? You need not have to remember the mathematics part of it. But remember what are those? What do you mean by lasso? What do you mean by reach? What do you mean by least angle regression, right? So that is one important part what we are going to discuss today. And your class exercise is basically run, because as of now you have run only these three, right? Run other four different models and try to see that how your model is getting created, right? Then the next part is how do you select your model, right? Adjusted R-square you have discussed so far, but other part we have not discussed. So there are other parameters which is, so that information criteria what we discussed, right? Probabilistic information criteria. So these are different parameters, different uh, kind of way to compare your models. Like adjusted R-square, all of us know more close to one. That means the explainability of the model is better, right? So like that, there are other parameters which helps us to understand our model better, compare our model. If I have two models and if one model has a better R square, adjusted R square, I generally select the better adjusted R square. But it only talks about the explainability of the model. What about the complexity? What about the bias? What about the variance of the model, right? So all those things will be taken care by other parameters. So we are going to discuss some of them today. So your class exercise is, once after today's discussion, when you run your model, try to run different models, the different selection processes, and try to compare your model by using other statistics that apart from your adjusted R square, right? So that you have a clarity that okay, what are those? Okay. So the data set remains same, that is your insurance data, right, which you have used earlier. So you have to predict your insurance profit, right? So this time I have mentioned what you have to predict. So your y or your response variable or your outcome variable remains same, that is profit for all of you. Other variables, independent variables, you have to take in your model. Okay. So first part is regularization or hyperparameter tuning, which is related to your this train validation and testing data set, right? Okay. So before that, how you like how a model, because for the equation we are not writing equation or we are not taking derivatives. But once we put our dependent and independent variables, the model itself is creating a equation for us, that y is equal to some constant plus beta 1x plus beta 2x2 beta 3x3 plus some error terms, right? So let's say this my model created y is equal to beta 0 beta 1x and error term, right? So y, which is my predict, which I want to predict, that is my response variable, is some constant plus this equation which all of us know. But the point is how that model knows it, right? Model that doesn't know mathematics, model doesn't know any equation or doesn't understand what is a regression, right? How it calculates that. So for that, you have to put in a mathematical equation, that is cost. Cost is what? Cost is nothing but our the error from your actual value with your predicted value. So if my predicted value is yi, sorry, actual value is yi, and my predicted value, if I talk about my prediction, this is my predicted value, beta 1 xi plus beta 0. The difference of that, right? I take a square, that is my that mean square error, right? Divide by n, that becomes my mean square error. Then the question is why you are dividing by 2. It is just a mathematical part where we put, because when I take derivative of this, right? Because see, remember, if some of you remember calculus, right? Whenever we are minimizing a function or maximizing a function, right? We take a derivative and try to see that when we're trying to find a minima or maxima of a function, right? We take a derivative and try to find out where it is minimum value, right? When I take a derivative of a square term, what happens? So 2 will come back to this side. So what if I take derivative of the numerator, what will happen? 2 times of this value. right? So to cancel out the two, generally in the denominator, mathematical, to make the calculation easy for the computer or that the running program, right? Automatically 2 has been added, right? There is no other benefit of adding 2. Otherwise, if you see, if I remove 2, it is nothing but my mean square error, right? The cost function is nothing but my mean square error, which I am trying to minimize. So I'm trying to create a model which will be in a such a way, which will be in a such a form that the difference between my predicted value and my actual value is smaller, as low as possible. I know that it can never be perfect because there will be some random issue. Think about in this way. If I'm a marketer, I can predict the sales. All the 100 parameters are available. Can I predict sales or revenue from a customer with 100% accuracy? Not possible, right? So there will be always certain things which is not in my control, right? And that error always will be there. Apart from that error, as a business person, I want to predict as much as possible, right? So, but how does, like, manually? I know that I'll create a derivative, I'll write equation wherever minima, I'll go to that point, and that will be my providing the minimum cost parameter, right? But when the model or the computer does it, or the program or the algorithm does it, so again, it start with like a child, right? So it just start with a child. It takes a random value first. So if you just look into this uh, curve with the red line is going on, so it start with a random line. So let's say if I have to put a line, a regression line, and these are my data points. This blue are my data point, right? So which this red line is showing. If you see in the beginning, it was in a horizontal. So it will start with that, and it will try to see that, okay, what is the distance between my measured point, what is the distance between my actual point and my predicted line. Then it will show that, okay, this is too much error. Then it will try to take it little bit closer, again little bit closer. If you see, gradually the line which is coming in your aim is nothing but your slope of this line, right? And b is the constant value. So it start with 0.00, slope is very low, slope is 0. Then it start increasing the slope. If you see here in the left side of gradient search, nothing but it is showing about the parameter of this line, your m value, that is slope. So if you remember the linear equation, y is equal to mx plus b, m is the slope of a line. So m keeps increasing, and it increases. At certain point, the increase rate gets slower, 1.40, 1.41, 1.42, like that. Finally it reaches a number where it knows that, okay, now the distance from line with the points are the actual values, line is the predicted value, is lowest, and that becomes my regression. That becomes the line which will predict my future point, or whichever point I want to predict. All of us, whatever we are going to study today, trying to find a line which best fits this point, cluster of point which is given here, right? So this is nothing but known as the gradient search, the step. Yes, Apurva.
Sir, you said over here the cost that we are finding out, it is actually the error that is between the actual values we have and the predicted. So, sir, is this cost the same as the epsilon that is there, that is used to find out the y over here?
Yeah, epsilon is the error term. Epsilon is the mostly it is the random error which you cannot able to find out. So that is
Okay,
the
sir.
randomness. This is only the
So, sir,
so
sir, the cost and the epsilon, both of them are different errors. They are not the same errors.
cost and the epsilon are different errors. Yeah.
And sir, over here in the gradient search, sir, there is also a value that is termed iteration, sir. As because I'm seeing m is also changing, the iteration is also what is iteration, sir, over
Iteration
here?
is the number of times the algorithm is running. So first time it ran, so m value and b value was something. So it saw that, okay, it is the distance between your predicted value and your actual value is too much. Then it runs again. So the number of times, iteration means the number of times the model is running your data to find your best possible value for your parameters. So if you see iteration numbers are increasing, it is the number of times the model is running your data. So think
Yes,
about
sir.
this.
So, sir,
So yeah.
yes, sir.
Good.
So, sir, as the iteration is changing every time, so we can say the model either is picking up more parameters for more accuracy, or maybe if there is a high collinearity between two parameters, it is also dropping off, or maybe
Yes.
trying to reduce the errors.
Yeah.
The parameters is also changing, the number of parameters.
Yes. So here it
every
is a
time we
very
try.
simple, because here it is only one parameter. You have only one predictor and one dependent variable, right? Think about a complex
Yes, sir.
model where you have only one dependent variable but 100 or 50 independent variable, right? So iterations will
Yes,
keep
sir.
increasing, because it might not be
Okay, sir.
possible to get the result within 100 iterations.
Okay, sir. Yes, sir.
And this is something again will come back when we get neural networks, because it has a lot of applicability in. So there are certain concepts on the batch size, iterations, because think about, so it is only 100 data points or 1000 data points. Iterations means every time your model, the algorithm is taking all the data, running it, then giving some result. How many times your model is running to give your final result? So here if you say around 140 or 150 times. So think about a large data set with lakhs of data points. If it has to run 100 times or 200 times, how much time it will take? And that is where you have to maximize. So that is where you have to think of how much effort or how much kind of energy you will put into running those models. Think about Amazon
Yes.
or Netflix. So they have millions of billions of data points. So there they will try to reduce the number of iterations. So
Okay, sir.
iteration simply means number of times your model is running to find the final equation. So if you see finally after one, how much? It will stop at around 200. It is going to give you the final equation, right? Which if you run in your ear, just manually, if you try to find, you might be able to find a lot easier than, lot faster than the model rather than doing it 200 times. But the point is, when you talk about more number of parameters, more number of data points, machine will be always fast. So now the
Sir,
problem,
I
what?
have one
Yeah,
more
yeah,
question.
yeah. Go
Sir,
on.
is iteration, the number of times the iteration value is increasing, sir, is it also somehow dependent on the accuracy of the model? As if there is more iteration numbers, like if like 200, one has 200 iteration value and another has 100 iteration value. So will there be any difference in the accuracy
Not
or
necessarily. It depends
efficiency
upon
maybe?
it depends upon. See, think about in this way. If I'm taking one computer or one algorithm is taking 100 like minutes iteration, just think about for each iteration it takes 1 minute. So what it means, 100 iteration means it takes 100 minutes to give me a solution. Another machine takes 200 minutes. Each iteration it takes 1 minute. So it, let's say it runs for 200 minutes. Though it never in minutes, let's say seconds, right? One machine is
Yes, sir.
100 seconds, other is 200 seconds. But you cannot compare the accuracy. It is only about the machine performance. If I have given a complex algorithm, one machine will take 200 seconds, other machine will take 100 seconds, right? But at the
Yes,
end,
sir.
the simpler algorithm might give me a better result. So it has nothing to do with accuracy. It is with the your model complexity, or it is with, let's say I have only taken two or three variables. So within 10 or 20 iterations, my model on the machine might give me a result. If I have taken 10 variables, it will go through a lot of permutation combinations. After 200 iteration, it will give me an answer, right? So the number of iterations depends upon the data size, how much, how big your data, how many data points are there, and the complexity of the model.
Okay, sir. Yes, sir. Understood.
So now comes the like most common question if you go to any kind of analytics kind of interview, that is a common question, that what is a bias and variance trade-off, right? So bias simply means how close to my, like what we are trying to calculate here is actually we're trying to calculate the cost parameter or the bias, how close we are to the kind of whatever the prediction. If you look into this, the middle picture, right, this is a high bias, right? Why it is high bias? Because if you see, the lines looks non-linear, right? But I have fitted a linear model. So if you see in each point the difference, right, if I add up, right, so my prediction values is not close to my actual values, right? In some cases it will be actually only 2 or 3 points, it will be meeting the actual values, but most of the point, most of the prediction what I'm making, it is not actually to the true value. So the definition of bias is the average prediction of our model and the correct value. Correct value is the actual value, right, which you are trying to predict. Model with high bias pays very little attention to the training data and oversimplifies the model, right? So the point is, it is just creating some very simple model which is not able to take care of all the predictions. Out of, let's say, if there are 20 or 30 points are predicted here, it is able to maybe predict 2 or 3 points with good accuracy. Other point it is not able to predict well, right? Think about your class performance. If I just take only one parameter, okay, what was your performance in your class 10th or class 12th, and trying to predict your kind of class performance, let's say in MBA, for 10 out of 350 students, maybe for 10 students or 20 students, I'll be able to make a good prediction, right? But for others, my prediction will not be that good because I have taken a very simplistic model. My prediction theorem or hypothesis is a person's MBA score or MBA CGPA is directly related to that person's 10th score or 12th score. So out of your 350 or 330 students, for 20 or 30 students, it might be true. I'm getting good result, but not for all, right? So that is where your high bias, that means whatever I'm predicting is not actually giving me a actual result, which is the actual value or the true value. Variance happens when, because see, always we are talking about the training data set and testing data set. Whenever we are predicting something, we are training our data set, training our model with the existing data set and predicting it for a new data set. Testing data set means what? That is a data set which I have not used in my model. So that data set I have only kept it aside. Whenever like kind of my model is ready, I'll run that, right? And same thing, I'm assuming that same thing will happen in the production environment, actual environment also. So variance happens when you are so engrossed in your training data set, right? Trying to fit a very complex, very like best model for your training data set. So if you see in the left side part, so I have for each point I have taken care. So I have started building model. I've started writing equation. I have written 100 or 1,000 lines of code in such a way that each point has been taken care of. So that for each point in my training data set, when I'm predicting, right, I have a very kind of low bias. If you see, for each point, my prediction is actually close to my like kind of whatever their actual value, right? So very low bias or zero bias. But what has happened there? My model has become very sensitive. Now what happens? I'm suddenly bring, let's say, in the test data set, there is a point which is not in this scenario. That is something away from these lines, right? Suddenly my model will not be able to predict that. My model will not perform in the testing data set. So when I say testing data set, whatever performance is it is giving in the training data set, it will be very high. So I'll think that okay, I have built a brilliant model. But when I'm telling my model to run with the testing data set, new data set, because new data set, no guarantee that it will be like this, right? So in that case, what happens? My model, most of the times it will fail in the testing data set. Whenever there is a high variance between your testing data set and training data set, right? That causes the problem of high variance, right? So now what happens? High variance will happen when you are building a complex model based on your training data set. Bias happens when you are building a very simple model, right? Not looking into other factors, right? So now the problem happens how to balance between that. So neither I can build a very complex model, because if I build a very complex model, it will perform very well, but it will not generalize. It will not perform in the actual data set when production or when the testing happens. If I'm building a simple data set, it will very perform poorly in the training data set. It will also perform average or poor in the testing data set, right? So that is the problem as a data analytics or a data scientist. You have to figure out how to keep this balance, how to make a model neither, so to like kind of quote Albert Einstein, everything should be made simpler as possible, but not simpler, right? So you have to build a model in such a way that it should be simple, right? Like if you remember in the first few classes we discussed, in some cases explainability of the model matters. I cannot say that okay, it is a black box, it is a neural network, I do not know how the model is calculating. In finance, insurance sector, in US and Europe, You cannot tell like that in today's world. You have to tell me that, okay, on which basis I'm predicting this my credit score, on which basis I'm rejecting somebody's loan request or accepting somebody's loan request, because I should not take certain variables which is sensitive in nature. So I cannot say that, okay, I will not, it is a very complex model, I cannot explain that, right? India, I think till now those regulations is not in place, but in outside country it is there. So now the problem happens, I cannot build a very complex model. If I build a simpler model, it is, so complex model will perform very good in my training data set. It will fail in the testing data set. Simple model will perform below average, right? Both in training and testing data set. Now what I have to do is I have to create a model, right? Which is like keep a balance between that simpler model. Think about simpler model. If I have taken this that same question what you have done, customer revenue, right? I build a very simple model. Customer revenue is zero point 0.2 times customers, 0.01 times customer income plus 200 rupees. Whatever is customer's income, that 0.001 percentage of that plus 200. So that is a very simple model. I'm not taking any other variable. I'm just taking customer's income, and with customer's income, I'm predicting what will be my customer's revenue. So if I have 16,000 data point and I start a equation like that, maybe for 2 or 3 customers or 10 customers, my equation fits perfectly. Exactly whatever I am predicting, it will be actual to actual value. But for rest of 15,000 data points, it will give very erroneous results, right? So that is the problem where I have a very simple model, or I can create a very complex model. Logarithm of customer's income plus let's say square root of customer's age multiplied by something like that. I'll build a very complex model, right? And for my training data set, all the information, the error, mean square error is very low, and I have a very good adjusted R square. But what happens when I run that same model in the testing data set? Because testing data set is a new data points. It is not in the range of your training data set. Then my model will fall. My model will not work properly. So that is the difference between your bias and variance, right? Bias happens when you have a very simple model. Variance happens when you build a complex model based on your training data set. So we have to be in between, right? Neither very complex nor very simple, right? So how do you handle underfitting? Underfitting is basically higher bias, right? Higher bias means you have very simple model, right? So it is not able to, so either get more training data or try to run your model with more as much as possible training data, adding features to training data. So don't, adding features means add one more variable, add independent variables, right? So your model becomes little bit complex, try to predict better, right? Increase the size and number of parameters in the model. So same thing, like kind of, okay, adding features is basically when you like modify that some parameters you try to modify. Adding parameters means you add more independent variables, right? Increasing the training time until cost function is minimized. So this is where I talked about, right? So you try to run with different samples, different kind of training data set you take. You resampling techniques might sometimes it is like kind of better utilized. Let's say I do not have chance to increase my more training data. I have only 100 data points or 200 data points. So what you do, you take different combination of training and testing data set and try running your model, right? Trying to see that, okay, what different combination of your dependent variable and independent variable is giving you a best result, right? So the out of all this, if you like kind of in reality or in practicality, the best method to go away from underfitting or high bias is to start adding parameter, make some transformation, to start adding new parameters, try to find other variables, other independent variables, which will help you to build a little more complex model which will work in reality, right? Handling overfitting, when you have a very complex model, you have taken all the transformations, all the feature engineering you have done, now you have a very complex model that is perfect for in your training data set, but you are failing when you are putting that into a testing data set, right? So that will work in a other way around. It is exactly opposite of underfitting. Reduce the model complexity. How it will work? Try to reduce the values with the low p value, so that your model will like compromise on the adjusted R square or the explainability, but at least the model complexity will come down. So it will have a equivalent result in your, so it might not be better. It is not that your performance will certainly go up, but at least it will be close to your training data set, right? Then there is something called regularization and cross validation. Cross validation already we have discussed, but again we'll repeat. So then the important concept of regularization. What do we mean by regularization? So what basically we are trying to do when a cost function we are trying to do is, right, minimize the loss whenever we have a given data with the model performance parameter, right? If you go back to cost parameter, so what we are trying to minimize is the difference between our prediction with the actual value, right? That is what we are trying to minimize, divided by average value n and divided by 2, right? Divided by 2n. So minimizing the loss or minimizing the cost function, right? Given the data with the model what we have created, right? So this is the meaning of minimize loss or minimize the cost with the given data point. Given we have created this kind of equation, or model is nothing but that regression equation what you have created. So now what happens when you talk about regularization, right? We are adding some term called complexity, because now we realize the model, when it becomes more complex, it will have a high variance, right? It will work very well in the training data set, but it works poorer in testing data set. So we are running a, or we are adding a penalty term for complexity of model. That means if you remember, that is the difference between R square and adjusted R square. That also works in the same direction. Whenever I add a additional independent variable, my R square value increases. That's why we started something called adjusted R square, which penalizes your R square whenever you add a new independent variable. Same thing here. We are adding some penalty because at the end we have to minimize this cost function and minimize this equation what we are trying to add, right? And this equation is nothing but the regularization term, right? So our training optimization algorithm is now a function of two terms, the loss term which was already there. Adding to that, we are trying to add another term which we are trying to minimize, which will minimize the complexity of the model, right? So let us try to understand through example, that will be better. Okay, I'll come back to this a little bit later on. What do we mean by L1 and L2 regularization? So this is my regularization term, right? So this, if you remember the left side part before the plus term, this is nothing but my cost function, right? So this same equation was there in the beginning. This is what I'm trying to minimize. I'm minimizing the loss, minimizing the distance from my prediction and my actual value. On that, I'm adding something called regularization term. So what you see, if you, this beta I square is nothing but the coefficient, right? So if I have, let's say, think about a very simple model, right? So what will happen? I have only one beta, right? So that same equation, what one y is equal to, if I go back here, what was the equation? Y is equal to, like, I think 1.49 or something. Let's say y is equal to 1.4345, 1.47, I guess. 1.47x plus 0.03, right? So let's say that was my equation. What will be my beta? If my equation is y is equal to 1.47x plus 0.03, so what will be my beta 1?
So 1.47.
Same thing, same equation, 1.47x plus 0.03, beta 0 is 0.03. Let's say I'm trying to find the cost function for that. If I have built that equation, right, what happens? So this is my cost function, 1.47x plus 0.03 minus whatever the actual values, right? For each of the values, I will have some actual value of y. Then I'll try to minimize this. So that was my cost function, right? On that, what I'm adding? Lambda. Lambda is something known as a hyperparameter multiplied by beta I square. So 1.47 square, right? If let's say I have a very complex model, 1.47x plus 2.53y, 2.53x2 plus 6.71 x3, write that. So now what happens? I have to add that those square also, 2.73 square plus 6.5 square. So now what happens? My cost equation becomes more weight, right? It becomes higher. So by adding this second part, which is in this square box, what I'm trying to tell that model, anytime you add a new variable, anytime you add a new independent variable to my model, I am going to penalize you with your whatever, like beta square. 2.73 x2 means these will get added by 2.73 x2 square. 6.73 x3 means 6.73 square will get added. So what will become, my cost function will become more, which I'm trying to reduce. So the ideally what I'm trying to do, it becomes zero. I am very happy, because whatever actual value I'm able to predict, but it will never become zero. It will have some value, right? I'm trying to minimize that. So on that, whenever I'm adding this parameter, which is that in the square box, so I'm penalizing that. Whenever you add a new beta, that means whenever you add a new independent variable. Same example what I was giving, my customers revenue is equal to 0.001 customers income plus 200 rupees. So that is my simple model. Now what I'll do, customers revenue is equal to 0.001 customers revenue plus square root of 2.3 square root of customers age plus 5.5 multiplied by customers gender. Like that, if I create a model, whichever those new betas are coming, right? Beta is nothing but the component which is multiplied to your parameter. So that square of that I'll keep adding to my model. So my model, this cost function becomes higher, which I'm trying to reduce, right? So now what happens, the model will try to only add those variables which is actually justifying the addition, right? Not necessarily it will keep adding. So it will not try to make your model very complex, because every time I add a new variable, new independent variable, my model is getting penalized, right? Same thing if you remember the difference between R square and adjusted R square, right? So this term is known as regularization. So lambda is something which is like what we discussed, right? So for different algorithms, there are different values of hyperparameter. There is different hyperparameter kind of definitions. So in this particular case, if you see like this lambda value in your model, you have to keep changing, and that is known as something as hyperparameter tuning. So this lambda which is multiplied, right, is nothing but hyperparameter. So what basically a data scientist or a data analyst guy does, so he runs some codes which will try to change this value of lambda, which will try to play with this values of lambda, try to build a, I'll not say a perfect model, but close to the reality model, right? Which model will work in kind of real terms, right? So how you play with lambda? Lambda can be something like Apurva was asking, something with the iteration, something with the batch size, something with the learning rate. So lambda can be how much. So if you remember, come back to this gradient, right? So if you see that initially, if you see this component of x, how quickly it is increasing. So each step it is taking 0.01, 0.2. If you see quickly, just again look into this right side of the graph. So it will start with 0.0x, and suddenly within few steps it will become 1, right? But once it becomes 1.30 or 1.31, then the step size becomes 0.01, 0.02, 0.03, right? So just observe how slowly it moves, right? So that can be one hyperparameter, the step size of your model, right? So there are different ways of hyperparameter. So hyperparameter is something which helps you to build this regularization term. And what is the regularization term? Regularization term is the penalty which you give or which you add to your model to make your model less complex, right? Because every time your model becomes more complex, complexity means you start taking more number of independent variables, right? It try to kind of penalize your model. Uh, any question or any doubt on this? After 10 minutes, please remind me. We kind of have a quiz. Okay, so
Sir,
yeah, go on.
sir, over there it was written plus lambda, the sum of beta and x. So over here, so what will happen if I change this plus to minus?
Minus means you are adding, you are saying that your model becomes more complex. It is very good.
Oh,
So,
okay,
so
sir.
if I
Okay,
take,
so the
so what is,
sign is going to affect the complexity, whether I'm going to make it more complex or not.
yeah, because our idea is to reduce the variance, right? To reduce
Yes, sir.
not that it has to be very simple also, but make sure that it is not too complex, right? If I minus it, so what happens? So this cost function minus this, my more the model parameters I bring, the cost function will come down. That means I'm building a very perfect model, which is not true.
Okay, sir. Okay, sir.
Right? So all those four things what we are going to discuss is nothing but how your equation of the second part of your regularization term or the regularization term is written. So if I just take the kind of absolute value of the beta, absolute value of the weight, right? Multiply it by lambda, right? So when I take this absolute value of this beta, right? That is known as LASSO or least absolute shrinkage or selection operator. Don't worry about that big name. Remember it as LASSO. So what we are trying to do is we are taking this. So if you remember, this is the equation, right? Yj minus xij. This is my prediction. This is what my predicting, and this is my actual value. So this beta, rather than beta, here it is written as weight or wj, right? So if I take and add it as a absolute value, right? So this is a lasso or lasso regression or L1 regularization. So whenever we are taking a absolute value of the parameters, absolute value of the coefficients and adding it to our model cost function, right? So that is known as L1 regularization or lasso. If L1 penalizes by absolute value of the weight, L2 is when you take a square of the weight, right? So that is a reach. So whenever I take a and add this parameter where I have taking a square of the beta or square of the weight, right? So then it becomes a L2 regularization or a reach regularization, right? And adaptive lasso is on the coefficient itself. So I add another weight. So if you compare between your lasso is what happens. This is the absolute value of your coefficient, right? So here what happens? Absolute value of coefficient, and on that parameter I'm adding one more weight. And how do I define that weight? Depending upon my prior experience, business experience. Let's say I'm trying to predict what will be a credit card usage of a customer, right? And I have one parameter, let's say on the gender, which I know that okay, uh, particular gender from a country, let's say females or males, have a high inclination of let's say spending, right? So based on my previous experience, right, data scientist or whomsoever is the manager, right, so they can add this additional weight, right? So this is different from your lambda. Lambda is chosen by your algorithm, step size, learning rate. So those are the lambda which is chosen by your algorithm, but this part based on your business experience you can add that, right? So this is a very recent 2006, which is again very new for if you in terms of data science, new algorithm or new way of looking into regression. Last one is no, okay. One is elastic net. Elastic net is a combination of L1 regularization and L2 regularization. So rather than taking only one way of looking into model, what it does is elastic net penalty is some alpha value, right? So that is again taken care by the model. Then L1 penalty. L1 penalty, if you remember, that is the absolute value of penalty, absolute value of your beta, plus 1 minus alpha into L2 penalty. That is weight square, the square of the weight or square of the coefficient. So it is a combination of L1 regularization and L2 regularization or lasso uh, and reach, right? Lasso is your L1 regularization, reach is your L2 regularization, right? Then next one is, or the last one is least angle regression shrinkage, right? Not getting into the mathematical part of it, the simplest way to understand it, right? Let's say I have two kind of predictors. Let's say I want to predict my customer income, and I have, sorry, I want to predict customer revenue. I have customer income and customer age. Okay. So when I first try to like start my model, let's say now I want to predict, right? So it will start with the least angle between these two. So let's say whenever I predict my value, if my value which is coming close to, let's say this x1, which is customer's income, right? So my line will be, obviously that is true, right? Everybody knows it. If my like correlation between, let's say, customers revenue is much correlated to your customer income, right? So more weight will be given to customers income. If I'm writing an equation and I know that my customers revenue is more correlated to customer income, so obviously that correlation is there and more weight will be given to my customer income, right? So same thing here. So if I want to predict y1, or y1 is, let's say, your prediction of your customers revenue, and x1 and x2 are your predict. One is x2 is, let's say, customer's age, and x1 is actually your customer's income. And when I find out that customer's revenue is directly correlated or highly correlated with customer's income, right? So the angle between, what will happen, the like line will be more inclined to your customer's revenue, customer's income, right? Or x1. Let's say these are two variables. When I add another variable, let's say I add another variable on customer gender or number of customer subscription count. If my existing line is more correlated with, let's say, subscription count, which is true actually, customers revenue will be highly correlated with customer subscription count, so that my line will move towards the customer subscription count. So like that, what happens, it will try to, so in geometry sense, it will, the your regression line will try to move towards the variables which are much more correlated to you, whichever value you are predicting. So let's say I start with my variable customer's age and customer's income, and I'm trying to predict my customer's revenue. Because customer's revenue is highly correlated with customer income, so it will go to the least angle between them. So the line will be drawn least angle between them. But when I bring another variable, which is customer subscription count, because I know that it is more highly correlated with customer subscription count, so my line will move towards the customer subscription count, right? So I'm not writing the mathematical equation, it becomes more complex. The simple way to understand is that the line or the variables which is more correlated to your dependent variable, right? So your regression line will follow that angle, so that is the least angle. Then cross validation. So this, what we discussed, if you have a smaller data set, right? So let's say I have 100 data points. Right now you have 16,000 data points or 1,300 data points. So you can build training, testing, validation data set. But you have a very small data set, 100 data point, right? So you do not have much option to, you do not have that much data point to create a different training, testing, validation data set. So what happens? So randomly 10 data points or 20 data points will be selected as validation. Then balance 80 or 70 data points will be taken as training. Then model will run. Then another randomly, another 10 or 20 data set will be taken as validation. Then others will become training. So what happens? Those using that only 100 data points, you are creating different models. You are running that 100 times or 200 times or 1,000 times, taking different data as training and testing, right? And at the end, what happens? You take the performance of the model equation, what you are writing, average of that as your final model. So performance of your complete or the overall model becomes the average of your each model. Let's say I created 5 models, so that is where it is known as k-fold cross validation. Number of folds you are creating, number of times you are iterating, right? Then any questions or any doubt on this? Okay, if not, we do not have much time, but I'll just quickly show you. We'll again put little bit of time in next class. So this is something, like I said, these are the few things. Don't remember the equation. I'm not going to ask questions on equation. Like adjusted R square, these are few parameters, right? Which helps you to kind of compare your model. Let's say I built one model with, let's say, LASSO, or another model with elastic net, another model with ridge regression. Which model is performing better, right? So in this case, these like whatever parameters, AIC, BIC, corrected AIC, right? So this gives me idea that, okay, whichever model is performing well. So remember, for all these criteria, so whatever is mentioned here, the smaller the value, the better the model. Out of, let's say, 3 or 4 model which I'm asking you to create, whichever model is giving me the smaller value, that is the better model. And there is something called Malus CP statistics, which will be again calculated by the, if you select that, it will be calculated by the model. But there, what you have to remember, best model should be the CP close to the P. What do you mean by P? So whenever you are getting this value of CP, try to find out that whichever model has the CP value. CP value you need not have to calculate. So that model is going to calculate for you. Is close to P. What do you mean by P? Number of predictors. If I'm creating a model with 6 predictors, another model with 5, another model with 4 predictors, right? So I have 3 different models, 4, 5, 6, and my CP value came at 4.12, right? So then I'll select the model with 4 predictors because that is close to 4.12, right? So this is only one difference between other parameters, which is the other is AIC, SPC, corrected AIC and SPIC, right? So don't need to remember the equation. I have shown you just for the like kind of for your information. Only thing what you have to remember that these are the parameters which like adjusted R square helps you to select a model. The lower the value, the better. And in case of malus CP statistics, the CP value closer to number of predictors that gives you the best kind of model. Okay. So we'll spend maybe 10 minutes or 15 minutes in the next class also. Okay. But that's all for today. Any last question?
Sir, I had a question, sir.
Yeah.
Sir, when you were teaching balancing the model over there, you were talking about handling underfitting. Over there, you had said that adding the features to training data.
Hmm.
So, sir, if I'm adding the features to training data, will that not create an asymmetry between the training data and the testing data? Or is it that if I'm adding,
Same thing has to be reflected in your testing data set, right? So whatever you are adding
so,
features, if I add a new variable, that has to be there in the testing data set also. If I add a new variable which is not available in the testing data set, it is not going to perform.
okay, sir. So if we are adding any parameters over there, so it should be there in the testing as well as in
Yes.
training, both of them.
Yeah, so and that is a big problem happens for this data scientist. So they might have taken a sample data set and build a model, but actually in production that information is never being gathered. If I just do a market research and take your income data, but when I put it into my production, let's say Amazon is not collecting your income data, that model will not work. So whichever parameter I'm taking in the training has to be there. That information should be available in the testing or the production.
And
Okay.
sir, one more question.
Yeah.
Yes, sir.
Quiz is
Sir,
live. Quiz is live. Go on. Yeah.
so the bias variance trade-off. So are we doing all these things that we are learning? Is it for the interpolated data, or can we carry it for extrapolated data as well? Extrapolation cases as well.
No. That's what I told you, right? Whatever model we are building, mostly it is for the interpolation or the prediction part within the range available. Extrapolation will have to have some other like things to be taken care of. So extrapolation
Yes,
generally
sir.
we avoid.
Yes, sir, because if we'll have extrapolation, there will be more. So we'll have
Yeah.
either high bias, low variance, or high bias, high
Yeah.
variance cases.
So our prediction will always possible within the range of data we have taken. If we want to predict something which is outside range, we have to give a higher confidence interval, right? So again, we can
Yes,
predict,
sir.
but the confidence interval will be too high.
Okay, sir.
Okay. Okay. Chalo, I prepare for the quiz. Any other doubts we can discuss in the next class. Take care. All the best.